We have covered 3 of Maxwell's 4 equations. Gauss's law for electricity, electric charges create electric fields. Gauss's law for magnetism, no magnetic monopoles. Faraday's law, changing magnetic fields create electric field. In 1820, Hans Christian Ørsted made a discovery that changed physics. During a lecture, he noticed that a compass needle moved when he brought it near a wire carrying electric current. He realized that electric current lines form circles around the wire. But we have not yet answered a fundamental question. How do we create magnetic fields in the first place? The answer comes from the 4th and final equation, Ampere's law. Here is the apparatus, a straight wire connected to a power supply. A compass sits beside the wire. The switch is open, no current. The compass points north, following Earth's magnetic field. Now I close the switch. Current flows. The compass needle swings. It is no longer pointing to Earth's north. It is aligning with the magnetic field created by the current in the wire. And the magnetic field lines are circular, so the needle points tangent to that circle. With no current, the filings lie randomly. No magnetic field, no pattern. Now I close the switch. Current flows. Watch the iron filings. They align into perfect circles around the wire. The magnetic field lines are concentric circles. This is the fingerprint of a current-carrying wire. Iron filings are tiny particles of iron that align themselves along magnetic field lines. Watch what happens when I sprinkle them around a current-carrying wire. The magnetic field created by a straight wire depends on the current. More current, stronger field. The field also depends on distance, twice as far, half the field. And it depends on a fundamental constant called the permeability of free space, mu0. The permeability of free space, mu0, is the value in a vacuum. But different materials have different permeabilities. Iron, for example, has a permeability about 200 times higher than free space. That is why putting an iron core inside a coil creates a much stronger magnet. The material itself amplifies the magnetic field. The direction of the circular magnetic field is given by the right-hand rule. Point your thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. This rule works for any straight wire. The magnetic field around a long wire is given by this equation. B is the field strength, I is the current, and R is the distance. Notice the field decreases as we move away from the wire. So the field is proportional to current, but inversely to distance. Here is a more advanced demonstration. 2 parallel wires on precision mounts. I can control the current in each wire independently, and I can measure how much they move. When current flows in the same direction in both wires, the wires attract. The magnetic field created by one wire interacts with the current in the other wire, producing a force. The force per unit length is proportional to the product of the currents divided by the distance between them. When current flows in opposite directions, the wires repel. This is how Ampere measured the magnetic force between currents. His experiments led to the mathematical form of Ampere's law.